In this video, we're going to take a look at related rates. This section are variables, are functions of time. Meaning our variables depend on t. So as a little warm-up here, if we take a derivative with respect to time of a function like x squared, well, x in this situation depends on t. So to get our derivative, we're going to take the derivative of our function x squared with respect to x. That gives us 2x. But to get our derivative in terms of t, we need to multiply by dx by dt. So this is really coming from the chain rule. It might be a little bit easier if you just let, say, f stand in for our function, x squared. Then all we're really saying is that to get the derivative of our function with respect to t, we take the derivative of our function with respect to x and then multiply by dx by dt. So that is the chain rule in action. One way to visualize this is you can just imagine the dx, the two dx's canceling out there, and you're just getting a little formula for df by dt. Now, often in our related rates problems, we will have several variables going on at once. So we may need to do something like take a derivative with respect to t of something like x squared plus y squared. So to do that, we'll first take a derivative of the x squared. So with respect to x, it would be 2x. But to get that derivative in terms of t, we need to multiply by dx by dt. Okay, then we go on to our second term. We can go plus derivative of y squared with respect to t is going to look like our derivative with respect to y, so our usual derivative, you can think of it that way, 2y. But to get this in terms of t, we need to multiply by dy by dt. And here I'm choosing y here because that's the variable that we just differentiated. We chose x in the dx by dt because that was the variable that we had just differentiated in that term. All right, so that's our main technique that we need to get a handle on before we can go on to a related rates problem. So with that in mind, let's try a typical problem here. So when a spherical ball is inflated, we know how quickly its volume is increasing. Let's say its volume increases by 800 cubic centimeters per second. We want to know how fast is its radius changing at a particular moment in time. So let's say when its volume is 4,500 pi, so 4,500 times pi cubic centimeters. So it might look a little bit weird to have 4,500 pi there, but we'll see that's really just to make the numbers work out a little bit more nicely. So we know the spherical ball is being inflated. We know how quickly its volume is changing. And we want to figure out how quickly is its radius changing at a particular moment in time. So first thing we can realize is that how quickly its radius is changing probably depends on how big the ball is at the specific moment that we're interested in. Well, let's see if we can organize our given information here. If we're talking about a rate of change, so how quickly something is increasing or decreasing, then we are talking about a derivative with respect to time. So when we talk about this number here, that's the rate of change of our volume. So we could write dv by dt. dv by dt is 800. It's a positive 800 because our volume is increasing. So increasing makes our derivative positive. If we were looking at, say, a ball that was being deflated, its volume would be decreasing, and we'd have to say negative 800. Okay, so let's say this is positive because V is increasing. So that's something that we'll have to be careful of in our problems, is just watching the sign of those derivatives. We could throw our units on here too, they'll be helpful at the end of the problem. So 800 cubic centimeters per second, rate at which the volume is increasing. The problem is asking us to figure out how quickly is the radius changing. So we'd like to find dr by dt, the rate of change of the radius. Remember, rate of change is always a derivative with respect to time. Okay, and we'll probably need a little bit more information to figure out this dr by dt, so we're told that we want to do that at the moment when the volume is 4,500 pi centimeters cubed. So let's find our dr by dt when V is equal to 4,500 pi centimeters cubed. Okay, and that way we've taken all the information in the question and just put it into mathematical notation. So now we're ready to start the problem. Now, often in these type of questions, the formula that we're going to start with is something that we need to come up with. So, formula for the volume of a sphere. This is a formula that we should be familiar with. V is equal to 4/3 pi r cubed, where r is the radius of that sphere. Okay, so once we've organized all our information, that's our next step, is to write down the formula that we're going to be working with. So our first real step in the problem. And second real step is to now take a derivative with respect to t. So take d by dt of both sides. Okay, so let's go ahead and take our derivative now. Derivative of the left side with respect to t looks like dv by dt. And derivative of the right side, this is now where we need to use the chain rule. So to take the derivative with respect to t, let's think about taking the derivative with respect to r first, and then we're going to need to multiply by the derivative of r with respect to t. So derivative with respect to r of the right side is going to look like 4/3 pi, so that's just all a constant that stays out in front, and then we're going to multiply by the derivative of the r cubed, so times 3r squared. So that is taking the derivative with respect to r, and then we need to multiply by dr by dt to really get that derivative in terms of t. So this comes from the chain rule, not a bad idea just to remind ourselves why we need to multiply by the dr by dt. Going back to the chain rule that we practiced right at the beginning of the video. So now, just to clean this up a little bit, we've got dv by dt is equal to, well, we can cancel a factor of 3 from the numerator and the denominator there, and we've got 4 pi r squared times dr by dt. Okay, so now we should start to be able to plug in here. We wrote down right at the beginning of the problem that dv by dt was positive 800. That's the rate at which the volume is increasing. Dr by dt, well, this is what we're trying to find here. So in order to find that, we're going to need to figure out what r is equal to. Now, we weren't actually given an r value in the problem. So what that means is that we may need to do a little bit of intermediate work to figure out the value of r. Remember, we were told that the moment in time that we're interested in is the moment when the volume is 4,500 pi. Well, we know that the volume of a sphere is 4/3 pi r cubed, and that should be equal to 4,500 pi. Okay, so this should allow us to solve for r then. We can cancel a factor of pi. We can also multiply both sides here by 3/4. So multiplying by 3/4, let's actually show that on there. Multiplying by 3/4, we'll just cancel the 4/3 there. So everything there cancels out. Multiply by 3/4 on this side. And if we grab our calculators here, we get 3375. Okay, and that tells us that our value of r that we're interested in is going to be the cube root of 3375. So we've just taken cube roots of both sides. The cube root undoes the cube there, and we're left with r equals cube root of 3375. If we try that on our calculator, r equals 15. So it works out pretty nicely. We had to do a few steps of work there to figure out our r value. Okay, so at this point we should be ready to plug in then. If we plug in everything, we've got 800 on the left side. We've got that's equal to 4 pi times 15 squared times dr by dt. Okay, so if we do a little bit more arithmetic here, if we multiply the 4 times the 15 squared, we get 900 pi, and that's times dr by dt. Okay, so now we can solve for dr by dt. Just divide both sides by 900 pi, and we can do just a little bit of simplifying here. Could actually cancel out a factor of 100 from the numerator and the denominator, and it will become just, oops, it's a little bit hard to read. It will become just 8/9 pi. So dr by dt, 8/9 pi. If you wanted a decimal expansion for your answer, you can try this on your calculator. Works out to about 0.28. Now in this problem we were given units in the question, so let's make sure that we give units in our answer. Remember, the best way to do this, thinking about our units, is to look at the units of your top variable, r. Well, the radius was measured in centimeters, divided by whatever the units of t are. So the units of t are seconds. So it would be 0.28 centimeters per second. All right, so a couple of observations here about this answer. First of all, dr by dt is positive. So that tells us that r is increasing. So yep, that makes sense in terms of our question, because what we were doing here was inflating a spherical ball. So we definitely expect our radius to be increasing, means dr by dt should definitely be positive. If dr by dt had come out to be negative, that would tell us that our radius is decreasing. Second observation here, you might notice that this number's fairly small. And the reason it's fairly small is that, remember, we're at a point in time when the radius is fairly big. The radius at this point in time is 15 centimeters. So this might correspond to your experience of, say, blowing up a beach ball. Once the radius gets fairly big, it's not increasing very quickly.